Alrighty, so welcome to our last class of April, if you can believe it. All I know is that April flew by a lot faster than March, which I'm very happy about. And I actually thank you guys for that. I think if I weren't teaching, April would have been another year-long month, kind of like March was. So, but anyway, before we get into our next topic, which is really just continuation of the same thing, looking at sine and cosine and all these guys. Are there any questions about homework or anything else that we've done up to this point? All right, hearing nothing and seeing nothing. I'm going to take that
Actually,
as a,
I
oh,
might have a question. I'm not sure.
okay, go
There
ahead,
was
Adam.
there was a problem on the homework that it was asking about a Ferris wheel,
Okay,
and the one of the answers it was asking for cosine,
okay.
and I understood how it worked because you can do it either way, but I was wondering if there was a reason why it preferred cosine in that situation because it was a negative cosine because instead of a positive sign, which I figured would be better because you start at the bottom and go up. So I don't know if you kind of get what I'm saying here.
I absolutely do, and I think I can answer that pretty well.
Okay.
Um, so let me actually go to the board and show you um, how I would decide which one to use. Before I go to the board, I just want you guys to realize, because this was a question that someone had in office hours too, um, it doesn't actually matter whether you pick sine or cosine, because either one of those will give you the same thing as long as you do a proper phase shift. Okay, so like if you're going to try to find the equation of a graph, and I know that this is slightly different than the Ferris wheel, but if you're trying to find the equation of a graph, whether you use sine or cosine, you're going to have the same amplitude, the same period, and the same vertical shift, bringing your midline up or down. Those three things are always going to be the same no matter which one you pick. But sine and cosine could give you different C values, different things that we're adding inside of sine or cosine. So that's really the only difference between them. And then you can also have the negative sine and negative cosine, which flip these things over. So there really are a bunch of options depending upon which one you want. So let's look at the board, look at the difference between the four main types. So cosine and sine and their negatives. And then we'll talk about how this relates to the Ferris wheel and why they probably chose to use negative cosine. Even though, Adam, you could have used sine or negative sine or positive cosine, like you can use any of them. You just have to phase shift properly.
And it
So,
would have taken it as a correct answer. It wasn't specifically asking for cosine. It's just the,
yeah, it should have taken it
okay.
regardless of which form it was.
Okay.
Which brings up another thing. If ever you guys are working on a homework problem and you're certain that you did it right and the computer is telling you no, send me a message so that I can go and look at it, because sometimes there are programming issues. There are fewer and fewer of them now that this has been around for a while. But every once in a while there are mistakes. And one of the guys who works at the college, Larry Green, who's my office mate, who normally I can just turn to and say, hey, fix this thing. I can actually send him an email and he can correct it if there's a problem. But it shouldn't matter which one you choose as long as your phase shift is correct. So let me go to the board so I can show you what I mean about different functions still will work, but there are some that are a little bit better choices than others. So think about the regular graph of cosine and the graph of sine. And I'm going to go ahead and draw them both here. So cosine, kind of the key to cosine is that we've got our maximum when we're at the y-axis. So this first one's a graph of cosine. So we get a peak at the y-axis, and then we go down to a trough, and then a peak, and then a trough, and it just repeats with a period of 2 pi. But that's what cosine looks like. So then sine, what sine does, of course, is the same shape. it just starts by going through the origin. And so one of the first things I always do if I'm trying to decide which function to use, because I have complete choice, is I look to see where are we crossing the y-axis. Because if we've got a maximum there, I'm going to pick cosine, because then I don't have to do a phase shift. If I don't have a maximum there, I look to see if I'm going through the midline. It's not always the origin if we've got a vertical shift, but it's always the midline of the graph. In that case, then I'm going to want to use some form of sine. Now, if you look at the negatives, think about what negative cosine would be or negative sine would be. You throw a minus sign out front, it flips it over. And so negative cosine, what it's going to look like is, again, same shape, it's a wave. It's just now it's got a minimum at the y-axis. So if I've ever got a max or a min on the y-axis, I'm going to pick one of the cosines. If it's a max, I'm going to pick regular cosine. If it's a min, I'm going to use negative cosine. And then negative sine, what that looks like if we were to flip this over, is the positive parts become negative and the negative parts become positive. So what we're going to see is something that looks like this. So notice how the positive part, this little hump of sine, is now underneath. The negative parts, like this dip, that becomes one of the humps. So this is negative sine. And so if we end up going through the midline, I'm going to use one of these two, either sine or negative sine. And the way I choose which one is to figure out what's happening as I go through the midline. Am I going down or am I going up? So if I'm going up through that middle, I'm going to use sine. If I'm going down through the middle, I use negative sine. And that's pretty easy to remember. Up is positive and down is negative. That kind of makes sense. Okay,
yeah, I see why that's a much better choice for the carousel now.
Yeah. So now think about the Ferris wheel problem. What we've got with the Ferris wheel, and Adam, you said something at the beginning where it was like where you're starting at the bottom, right? Is that what it said in the problem?
I'm sorry, what was that question again?
In the problem, did it say that you're starting at the bottom of the Ferris wheel?
Yeah, that's why now I'm realizing, because yeah, the offset would be the center of the Ferris wheel, and then you're going up completely all the way. So it makes sense now.
Right. So that's why we're going to use this, because if you think about it, if this is a graph of our vertical position with time, so I'll even put on here time. So at the start, so at time 0, we're at the bottom of the Ferris wheel. As time goes on, we start going up, right? And it feels a little bit weird to think about it this way, but think about you're in the cage of the Ferris wheel. As you move along this circle, you're going from a low point and you keep going up, 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 until you reach a high point. Then you're going to come back down. So you reach a low point, high point, low point, and so on. So since we're starting at the bottom, a graph or a function of negative cosine will make it so that we don't have to do a phase shift. So that's why they, and me too, would go with a negative cosine. But if you don't see that, it's totally fine, because you could use regular cosine, regular sine. They would just have to require phase shift. So this is something else I told the person who came into my office hour earlier today. If you're one of those people that likes to have a, this is always how you do it, right? You like to have a recipe, then always pick cosine, regular cosine, because it's really easy to spot phase shifts. Because think about this, if this is the graph I wanted, if I had a graph of cosine where the max was up here, all I have to do is look and see how far does the maximum move, and that gives me my phase shift. So it's really easy to spot phase shifts on
positive cosine. So if you want a always do it this way, then go with positive cosine and just look to see how far does that peak have to move. And you can go either way. Like I showed it going to the right. We could have gone to the left. That's fine too. But you just have to figure out how far you move over, and then that determines your phase shift, and you're good to go. Anyway, so is that better for that one, Adam?
Yeah, the only thing I'm now thinking is if you did it if you did negative cosine without a phase shift, aren't you starting in a negative, like below the ground?
You would be unless you do a vertical shift.
Oh, okay. So yeah, right.
Right.
Okay.
Because I don't know what the numbers were, but let's say
Yeah, it was like
that this
50 or
has a
something like
radius
that.
of like 100 feet. But we're going to still be, say, 10 feet off the ground. So what this would tell me, the 100 is going to give me my amplitude, because from that mid, I'm going to go up 100 or down 100. So I would have minus 100 cosine of whatever, but I'll just leave it as a b. That would be determined by how fast the wheel is going around. But then I would need to have a shift upward, and that's a question of where the midline is. And in this example, it would be plus 110, because I've got my 100-foot radius and I'm 10 feet off the ground. So this is going to make it so that you don't go negative. But you're right, if it's just plain old negative cosine or positive cosine or any of the four, it is going to go negative at some point, but that's what we use the vertical shifts for.
Cool. Thank you.
Yeah, you're welcome. So anything else from the homework?
All right, well, it sounds like we're good. So we're going to go ahead then and keep moving along in our investigation of these trig functions. And the next thing we're going to do, the next thing we're going to look at is actually taking these things and going backwards. So you think about the trig functions, what they do is they take an angle and they give us a number. And that number is determined by the unit circle, and whichever trig function we're doing, we use the right ratio, right? But these things go plug in an angle, get out a number. But what we really want to be able to do is go the other way as well, because think about an applied situation. There are lots of times we want to find angles. And in fact, if we go back to the idea of trigonometry, remember we're measuring triangles and we're looking for two different measurements. One is side lengths and the other is angles. Well, we need to be able to get angle values somehow. And what we need then is to create something that goes backwards. So we need to take these trig functions and run them in reverse. So I'm curious if you remember, because I know you've seen these in places. You remember what we call functions that go in reverse? There's a name for them. All right, so Amber just typed in inverse, Kai as well. Yeah, so these are inverse functions. So functions, they take you from, X to Y. Inverse functions are going to take you from Y back to that original X. So places you've seen these. Exponential functions, their inverses were logarithms. Square root functions, their inverses were square functions. All right, you could have a function where you add a number. The inverse of that is going to be where you subtract a number. So it's just going backwards. So that's what we're going to do today is we're going to create the inverse trig functions. So these are going to be ones that you plug in the value and you end up getting the angle. All right, so that's our goal. We're going to look at inverse functions, inverse trig functions. So before we do that though, I want to remind you about inverse functions, just how they work and what goes on, because we need to have a pretty good understanding of that before we can see how to develop the inverse trig functions. So I'm going to go back to the board again.
So inverse functions, first of all, the notation that we use, just to remind you, is the little -1 power. So when we write this is the inverse of f of x. So just to remind you, I want to make this perfectly clear that when we write this, f to the -1, this does not equal 1 over f of x. Those are not the same. So it's not actually a -1 power. It's just the symbol that we use to say that this is the inverse. Okay, so this is what the notation we're going to use is for f inverse. Now, the way these work, I like to have pictures. I call this the island picture because these are like 2 islands in the ocean. And basically the way inverses work, f is a bridge that brings you from the island on the left to the island on the right. So there are a bunch of different x's in here, and each one of them gets transported to the other island with this bridge. But it's actually like a moving walkway. It's a one-directional bridge. You can only go to the right. Okay, so it takes us from some x here and brings us to some y on the other island. So what f inverse does is just the return trip. It brings us the other way so that it will return us back to where we started. So it's a return trip. Well, notice that this island on the left, this is the domain of f. And on the other side, this other island is the range of f. But for f inverse, those roles swap. Now, this island that's on the right is the domain, and the one on the left is the range. So those roles swap just because that's what domain and range are. It's the things that we're plugging in and the stuff that we're getting out. All right, so this might feel a little weird, but this is super important because what we know is the domain of one is the range of other, and we're going to make use of that in a minute. Okay, another thing that we know about inverse functions is what happens when we compose them. So does anybody remember what happens when we compose 2 inverses? Composing means plug one into the other. And in case you're not really sure what I mean, this is what I'm talking about. So we're going to do f of f inverse, or f inverse of f. So does anybody remember what happens with those? All right, so Amber just said they undo each other. That is definitely true. Well, what that means with both of these is that what we get is x. It just brings us back to where we started. So if you think about it, like this first one is saying we're taking x, we're putting in f inverse. So we went from this right island to the left island. And then when we do f, it's the return trip, and we're back to where we started. So we end up coming exactly back to where we started when we compose them. All right, a couple other things about inverses that are probably good to remember. Does anybody remember how their graphs are related? There's something special about their graphs. All this horrible stuff coming back from algebra. Okay, so Juan just put they're symmetric. Yeah, their symmetry. These functions, the graphs of f inverse, do have symmetry. And the symmetry that they have is that they're symmetric over the line y equals x. Your graphs are symmetric. over y equals x. So y equals x, that's the diagonal line. Pretend that's a line, so y equals x. And so whatever we see with the graph of f, so an example would be something like an exponential. Let's say we have an exponential function. What we do is we just pretend that this y equals x is a mirror, and we would see the other function look something like that. So imagine if I were able to fold the whiteboard or fold a piece of paper, the graph of one would overlie the graph of the other. So let's call this guy f. Inverse. All right, so that's the symmetry of their graphs. So the question is, why does that happen? Sometimes people are curious. If you are, the answer is that swap of the domain and the range. That means the x and y coordinates on the points of the graph get swapped. And so that's why these things show up. Okay, we just swap over the line. All right, so Amber says, how do inverse functions relate to everyday life? How much time you got? And that's a little facetious, but not really. If you want to know where inverses, yeah, if you want to know where inverses are used, oh good Lord.
Basically, we use inverses anytime we want to go the other direction. Anytime, I think of it like Jeopardy. You know, when you watch Jeopardy, you have to phrase things as a question, right? Like, what is the Great Wall of China, right? So basically they're saying they're giving you the answer and you're finding the question. Well, that's what inverses do, right? We teach you a lot in math about you start at point A and you go to point B, right? You go here, always going from A to B, A to B, A to B, A to B. As soon as we want to go the other direction, that's where we need inverses. So they're going to apply everywhere regular functions apply, just going in reverse. Let me give you an example just from trig. So we've been talking about these sine functions, and we can actually maybe use them to describe a path of a wave, like a real wave, like a physical wave, like a water wave. Okay, so inverses, what those are going to do is, what if instead of us knowing, right, instead of us knowing the equation, what if instead we knew how some particle of water was moving? What we need to be able to do is go backwards and find the equation. And that's what an inverse function is going to do. So in terms of specific applications, you'll see specific applications to the inverse trig functions. So here's an example. Now here's another good example. So think about those shadow problems. Remember when we would do here's the shadow of a tree, and we know that the sun's at an angle of elevation of 17 degrees, blah, 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 blah. What if you don't know the angle of elevation? What if that's what you're trying to find? The inverse trig functions are going to do that for us, because what we can do is say, oh, we know maybe the tangent of that angle, because we know that Bruce is 6 feet tall, and we just measured that his shadow is 8 feet long. That would allow you to find a tangent. And so we know the tangent of an angle is 3/4. The inverse function is going to let us figure out what that angle is. So it's really just going to give us a way to answer other questions. So, all right, cool. All right. So one other really important thing about inverses is this. How about, I'm going to ask class. First of all, do all functions have inverses? Yes or no? Thumbs up, yes. You can give me the clap if it's a no. So all functions have inverses, yes or no? Or you can type it into the chat. So I'm seeing some thumbs up. I'm seeing one clap so far. There's another yes that came in the chat room. All right. So for those of you who have voted, right? So for those that have voted, this would be we're voting yes as a group. Right? Well, unfortunately, we as a group would be wrong. Not all functions have inverses. Yeah, Benjamin, uh-oh. All right, so what do you mean not all functions have inverses? Well, do you guys remember the horizontal line test? And you probably remember the vertical line test. Like the vertical line test is how we check to see if something's a function, right? If a vertical line intersects the graph more than once, it's not a function. Well, think about that. Think about a graph that wouldn't be a function, but when we flip it, is. Right? Let me draw one on the board here real quick.
And I'll do a shape that you know pretty well. Let's say we're just looking at a semicircle. Okay, but I'm going to look at the semicircle that's right over here. So it's just the top half of the circle that's sitting over in this area. And this is definitely a function. It passes the vertical line test. Okay, everything is good. Any vertical line only intersects it in one place, because for something to be a function, when you plug in an x, you can only get one y, right? There can't be an or. Well, let's flip this over the line y equal x. So think about what this would look like if we were to fold the paper over. What we're going to see now is a semicircle that's on its side. And this fails the vertical line test. So this thing right here is not a function. So that means that whatever this function was that we started with doesn't have an inverse function, because when we flip it, we get something that's not a function. And so this is where the horizontal line test comes in. Since when we flip it, horizontal lines become vertical lines, for this inverse to exist, the vertical line test has to apply, which means the horizontal line test for our original function has to apply. We called that one-to-one function, if you remember that name. A function is one-to-one if it passes the horizontal line test. So functions can only have inverses if they're one-to-one. All right, so unfortunately, we as a class were wrong, but that's all right. That's why this isn't a democracy. It's a benevolent dictatorship. I let you think you have control until I need to take it over. That was a joke, by the way. I'm sorry. I'm in that kind of mood today. All right. So in order to have a function, for a function to have an inverse, it must be one-to-one. So let me put that up on the board because this is super important. So the shorthand for one-to-one is 1-1. You haven't seen that before. Okay, so a function can only have an inverse if it is one-to-one. If it's not one-to-one, it doesn't have an inverse. Okay, so this is where, if you're kind of paying attention and you're thinking about where we're heading, this is where you should start being concerned.
So why am I saying that? Why am I saying that now we need to be a little bit concerned here? Well, think about our goal, right? Our goal is to have an inverse sine and an inverse tangent and an inverse everything else. Well, think about what we were talking about last time. The graphs of these functions. Which of the 6 trig functions are actually one-to-one? Which of them pass the horizontal line test?
Tangent.
All right, tangent. Well, how about, let's start here. Does sine? Sine should be a pretty quick, no, it doesn't, because you think about that wave, right? You think about that wave. There are lots of horizontal lines that intersect it in more than one place. In fact, you take any horizontal line between plus and minus 1, and it's going to intersect that graph an infinite number of times, right? So sine is not 1-to-1. And so then, of course, cosine isn't either. So already that tells us, well, shit, we can't get an inverse of sine or cosine. Okay. So then what about tangent? So Adam threw out tangent. Kai just threw out no, none of them are. So think about tangent. The one piece of tangent is for sure 1-to-1, but then we copy that. Well, as soon as we copy, we're no longer 1-to-1 because there's going to be multiple instances of the same value. So when I first asked you which of the trig functions are 1-to-1, the answer is none. Not a single one of them, because they repeat. So periodic functions, just by definition, cannot be 1-to-1. Periodic means they repeat, and any kind of repetition is going to make it so that they fail the horizontal line test. Okay, so that's what I was saying, that if you've been paying attention and you kind of see what's going on, that this is a problem. We're trying to do something that we cannot do.
Bruce, what if you're not talking about like waves, if we're repetition? Then we're not really talking about the same thing either way.
Well, any of the trig functions repeats just by the nature of them.
Okay.
Right? Think about how we define them. We define them on the unit circle as we're spinning around in a circle.
Right.
Right? So take an angle. It's going to have a given sine, cosine, tangent, cotangent, secant, and cosecant because of the point on the unit circle. At some point as we spin, we're going to come back there. And as soon as we're back there, we're getting the exact same trig value a second time. A third time, a fourth time, a fifth time, right? We're going to just always get them. And so unless we restrict where we can rotate, then no, they're going to repeat, even though those other graphs are not sines or they're not waves, right? So as a whole, these things, they are not invertible. Okay, so let me tell you a little bit about mathematicians. We have some interesting qualities. First and foremost, we're lazy. Like, we're terribly lazy. That's why we have all the shorthand notation for everything, and we're lazy. Like, we'll do work, but we'll only do it once. And then once we see that we don't need to do it anymore, we don't. And we, you know, if something shows up over and over and over, we just, all right, so we're lazy, first and foremost. A second fact about us that not a lot of people know, because unless you live in this world, you don't realize it, but we are like ultra competitive. And that probably surprises you, because most people think about mathematicians as just, you know, the nerds who can only look at their shoes and, you know, don't want to talk to each other and all that. And while all of that is also true, we're also highly competitive, and we hate being told you can't do something. Like, someone comes and tells me I can't do it, I don't like hearing that, and I'm going to do everything I can to prove you wrong. And this is a pretty common theme in terms of mathematicians. So think about what's going on here. I just said, hey, I want to make an inverse. I want to be able to go backwards. I want to find an angle given a sine value. And then you come at me and you say, nope, can't do it. Your function's not 1-to-1. I immediately go to the, yeah, I can. I'm going to figure out a way. I'm going to make it work because I want it, and you're telling me I can't. Now, if you go, this doesn't sound real. Have you ever heard of I? Square root of -1? What's the number that when you square it gives you -1? Oh, there's no such number. Sure there is. I'm going to call it I. Well, I mean, it's not a real number. No, okay. But it's there. It exists. Right? We do this sort of stuff all the time in math. So here's what we're going to do. We're going to work around this. We're going to go, okay, yes, you're right. It needs to be 1-to-1 for this to work. I'm going to make it 1-to-1. And I'm going to make it 1-to-1 by ignoring the parts that don't make it 1-to-1. And I think, Adam was kind of already getting on this when he said, well, what if you just don't have the repetition, right? Like, don't think of it as a sign. That's what we're going to do. We're going to take these things and go, you know what? I don't want the entirety. So how about we just forget about the bits that don't work and restrict ourselves to that region? So let me show you what I mean with the graph of cosine. So let's go back to the board.
So I'm going to draw cosine. By this point, you should be feeling pretty good about how these things look, but here's the graph of cosine. All right, so what I need is for this to be 1-to-1 so that it would pass the horizontal line test so that I don't get the same values twice. All right, so I'm going to do this by erasing. I'm going to erase pieces of this graph that don't fit what I want. Right? I mean, this is great. This is like revisionist history. I'm just going to make it be what I want it to be. Tell my story the way I want it to be told. So instead of having all of it, the first thing I'm going to do is I'm going to erase everything but one period, because any extra periods are obviously going to be a problem. So I'm just going to erase all of this. If I had more to the right, I would erase all of it as well. But the first thing I'm going to do is just restrict myself to one period. Okay, cool. But now when I look at this period, recognize that this is not 1-to-1 either. I'm still getting some of the same y values multiple times, right? Like, think about this point right here. There's another angle with that same y that's somewhere later in my period. So I don't want that point either. I can have one of them, but I can't have both. So basically what I want is every single one of the outputs, everything between plus and minus 1, exactly once. So the way I'm going to do this is I'm going to start with my max. I'm going to go down to my min. And then at my min, I'm going to erase. So if we were to look at this piece of cosine, this piece of cosine is 1-to-1. It also gives me all of the cosine values. I get every value between plus and minus 1 somewhere in there. And that's what we're going to have to do every time we do one of these restrictions, is make sure that we get all of the values only once. Okay, so what angles do this? What angles give me this piece of my graph? I mean, obviously this is an angle of 0. And let's go in radians. How far do I go in radians until I hit my min in cosine? All right, cool. Get a whole bunch of people throwing up pi. So that's exactly right. Once we hit pi, we've gone as far as we can go. Remember, the 0 is at pi over 2. Right. So in order for this to work, for cosine to have an inverse, we have to restrict it to this interval 0 to pi. So this is a modified cosine. Now what I've got is a domain that's only 0 to pi, but I still get my range of minus 1 to 1. Right, because regular cosine has a domain of all real numbers. This one we're just going to restrict it a bit. All right, but now that I have this, I can create an inverse. And so the inverse function here is called inverse cosine. So that's the name of this function. It's inverse cosine. The notation we're going to use is cosine with the little -1 after the cosine of x. So it's kind of like when I showed you in the Pythagorean identity how we put the exponents in here. We show the inverse in here as well because it's telling us it's the inverse of cosine. All right. And so this is our function, inverse cosine. All right, so what about its domain and range? Well, this is where we're going to make use of the fact that the domain of a function is the range of the inverse and vice versa. So remember up here where we had our restricted domain with this range? Swap those, and that's the domain and range of inverse cosine. So inverse cosine, you can plug in any number you want between -1 and 1. And what it'll do is spit out an angle between 0 and pi. Which angle it gives you? Well, that will be the angle whose cosine was the number that we just started with. So let me show you how this works. It's not really that hard, and we don't really have to learn anything new. Like, think about your chart. Remember your chart that had all the different angles and then the trig function values. Now we're just going backwards. We're taking the column under cosine and we're backtracking to what angle would it be. So for example, let's say we had cosine inverse of 1 over √2, or √2 over 2. So this is saying, give me an angle whose cosine is √2 over 2. And if you look on your chart, there are multiple places where that happens. There's one very near the top, and there's one very near the bottom. But we need to get one that's between 0 and pi, so it would be in the top half of your chart. And so the answer to this, of course, then is going to be pi over 4. Because we know the cosine of pi over 4 is equal to √2 over 2. If we had a negative angle, so let's put in, say, -1/2, or not a negative angle, I'm sorry, a negative value. We know that still that's in our domain. It's between -1 and 1. So this is again asking, give an angle whose cosine is -1/2. Just make sure that angle is between 0 and pi. So there are a bunch of angles that do that. There's only one angle that does it between 0 and pi. So can anyone tell me what angle this is going to give me? Maybe type it in the chat, or if you want to throw your voice. So Amber just said 2 pi over 3. Kiva wrote 120, assuming degrees. Yeah, okay. And so, and those are the same, right? 120 degrees is the same as 2 pi over 3. And that is correct. Again, if you look at your chart, if you run over from 2 pi over 3 over, you see the cosine is -1. All right, so no big deal, right? But that's what these are going to do. They're going to allow us to get angles out knowing the trig function value. But we had to be sneaky. We had to restrict the domain. We had to look at this and go, well, I can only do that for 0 to pi, which is going to have consequences for us later. Okay, so just I want you to realize that this is super important. The restriction on this range that's from 0 to pi matters a lot. All right, so there's the restriction for cosine. Now we're going to have to do something similar with sine and with tangent. And so let's take a look at those and see what kind of restriction we're going to do in order to make them work. So let's look at sine and do the same thing that we did before. We're going to start with the graph of sine, and we're going to start erasing. Okay, so I've got a lot of stuff that I don't want, right? And so the question is, how can I erase this so that I get everything between plus and minus 1 exactly once? And the answer to that is, well, there's lots of different ways we could erase it. We basically just need to keep some piece that goes from plus 1 to minus 1, or from minus 1 to plus 1, or minus 1 to plus 1, plus and minus, you know, so we got a ton of choices. So the way that it was decided was that we're going to erase everything but this piece. Because just like with the cosine, this is going to give me all of my values exactly once. I've got everything between -1 and +1, shows up exactly one time. That is now 1-to-1, which means an inverse exists. Now, it might feel kind of random how we're deciding to keep this, but it's not at all. First of all, what would the different angles be for this one? What's the range of angle values that we can use to plug in here? How about, can you tell me where the max occurs? What angle gives me a maximum in radian for sine?
Isn't it half pi?
It is half pi. It's pi over 2. This guy's pi over 2. So then from the symmetry, we know that this would be minus pi over 2. So this one we have a different restriction, but it's the same idea. So let me just copy this down. Now if we do sine inverse instead of cosine inverse, the domain is still going to be -1-to-1, because those are the numbers that come out of sine. But now our restriction on our angles is going to be from minus pi over 2 to pi over 2. So it's a different restriction, but that was necessary because this is now sine. All right, so why this interval? Like, I think the cosine one, everybody seemed pretty good with because we started at 0 and we just went. This time we didn't start at 0 and just go. I mean, we did once we got to pi over 2, but then we stopped. And then we kind of backtrack and fill this bit in. All right, well, here's why we use these restrictions. Is think about this in an applied setting. If we're going to solve triangles, the most common angles we're going to get are between 0 and 90 degrees, or 0 and pi over 2. And so those are first quadrant angles. And so all of the inverse trig functions, we're going to pick intervals that contain the first quadrant. And then we're going to extend that interval in either direction so that we get all of the y values exactly once. So there is a little bit of rhyme or reason why this is done. But for inverse sine, these are the restrictions. But it works pretty much the same way. We're now going to plug numbers into inverse sine so that we get angles. It's just those numbers were the sine values. So let me change some numbers up here, and we'll do a couple for inverse sine. So we can have, say, inverse sine of √3/2. So we need an angle whose sine is √3/2. That's somewhere in this interval. So what angle is that going to be? You should be able to find it on your chart. This is one of the ones you should know. All right, so Mariola just put up pi over 3. Thank you. And that is exactly right. Inverse sine of root 3 over 2 is going to be pi over 3, because the sine of pi over 3 is equal to root 3 over 2, and that's the angle that's in this interval. All right, what if it was negative? So let's go to sine inverse of negative root 2 over 2. So again, you want to look at your chart and figure out what angles give me a sine of minus root 2 over 2. So if you looked at your chart, you'd see that they are 5 pi over 4 and 7 pi over 4. But the problem is neither one of those is in this interval. So what we need to do is be coterminal to it. Well, let me help you out a little bit. For this one, for inverse sine, remember how 0 to pi over 2 is a quadrant 1 angle? Minus pi over 2 to 0, this is a quadrant 4 angle. Because negative, we're rotating down. So we actually need a quadrant 4 angle. So if you go look at your quadrant 4 angle, you see 7 pi over 4. Well, that doesn't quite work. So what we do is we subtract 2 pi. And what you would get is negative pi over 4. Now, I know I just kind of talked through that, and a lot of you, it probably went right over your head. And you're like, oh my God, I'm never going to be able to remember this. So let me give you the how you do this. What if it had been positive root 2 over 2? What would the angle have been? All right, so Mariel just put up pi over 4. Yeah, it'd be pi over 4. Well, notice that this is a negative, and it gave us the negative pi over 4. That's all you got to do. Figure out what would it have been if it was positive, and then change the sign. Done. It's that easy. So you guys catch that? Let me show you another one. So what if we had, say, sine of minus 1/2? Well, I know it's going to be negative. And then I think, well, what angle gives me a sine of 1/2? It's pi over 6. So this is negative pi over 6. So in some ways, inverse sine is actually easier than inverse cosine, because you literally only need to know those first quadrant angles. You just slap a minus sign on it if it's negative. All right, so there's the restriction for inverse sine. But again, notice that we created an inverse function. We just had to be sneaky about it. We had to ignore the pieces we don't want. All right, well, let's do tangent, because if we've got the big 3, then we should be good, right? So what about inverse tangent? Well, we'll start the same way, which is draw a graph of tangent and then ignore the bits that we don't want. I find this really pleasing. I don't know why. I really like ignoring bits that are trivial. Right? So I think it's just sort of my contrary nature. It's my mathematician, right? I'm a little competitive. So let's think about tangent. And again, the graph of tangent had those little branches that kind of look like this that repeat every time, right? So we have this picture where the vertical asymptotes were. So those were at the odd half pi's. So this was pi over 2. This one was minus pi over 2. Out here would be 3 pi over 2. and so on, right? So those are kind of the delineators of our branches of this guy. Okay, so we need to think about where are we going to restrict this so that we get each piece exactly once, or each y value exactly once. All right, so where do you think we want to split this? Anyone want to make a guess what interval we're going to use?
Negative pi over 2 to pi over 2.
Okay, so Hava, thank you for that. So she says, how about minus pi over 2 to pi over 2? So that would be in between these two asymptotes. So you think about that piece. That piece does cover all of the different values that come out and is definitely 1-to-1. And then also, if you think about the other thing that we're now concerned about, that we want first quadrant angles, it does give us the stuff between 0 and pi over 2. So that is where we restrict our tangent. So we erase all that other stuff. And so here's our modified tangent. So the modified tangent, in terms of its domain and its range is still all real numbers because we don't change that. But we did change the domain. But it's now between minus pi over 2 and pi over 2. But I do want to point out that there's a huge difference here. I put parentheses instead of brackets because I don't get to plug in minus pi over 2 and pi over 2. The tangents were undefined there, hence the vertical asymptotes. So we have to make sure we put parentheses on there. Which means then for tangent inverse, its domain will be minus infinity to infinity. So if I've got tangent inverse of x, I can plug any number I want in, but the numbers that come out are between minus pi over 2 and pi over 2. So it's virtually the same restriction as with sine. It's just we have parentheses instead of brackets. Which means we're going to do exactly the same thing for inverse tangent. That if it's a negative, just think about what would give you the positive and then slap a minus sign on it. All right, well, cotangent, there's an inverse cotangent. Secant and cosecant, there are inverse secant and inverse cosecant, but I'm not going to go into that because really all you need are the big three, right? Like if you told me, hey, find an angle whose tangent is 5/3, or sorry, whose cotangent is 5/3, I'm just going to flip it over and go, oh, the tangent is 3/5. Now I'll use inverse tangent. So there's always a way to get to the one of the big three if we just, do the reciprocal stuff. So that's why we don't care about so much of the other three and their domain restriction. All right, well, we were successful. We successfully created inverse functions where we weren't supposed to be able to do so. So that's kind of good, right? I mean, now we're going to be able to go backwards. So let me show you. Let's actually get to a real example because I know you guys want to see that, right? Most of you are not mathematicians. Most of you aren't in this just because it's cool. You want to see why we care. So let's say we're measuring a triangle. And specifically, let's go to that shadow question. So here's this deal. Let's say it's a bright sunny day, right? And we measure that my shadow is 8 feet long. So I'm standing on the road. It's nice and flat. So you guys take tape measure. You put one end at my feet, and then you measure my shadow down here on the ground. And you measure that that's 8 feet long. Now, what you may not know about me is that I'm 6 feet tall. I'm slightly taller, but we won't go to an extra inch because that'll make the numbers weird. but I'm 6 feet tall. And so here's my question to you is what is the angle of elevation to the sun? So if we were to actually think about this guy right here, I want to know what is that theta? Now in
30,
essence,
30 degrees.
I'm sorry, say again.
I think it's 30 degrees.
30 degrees? We'll find out real fast. But in essence, I'm asking you to solve this triangle. And we've already seen that the trig functions are the links between angles and sides. But notice what's different now is I'm not giving you an angle. I'm giving you just sides. So here's how this would play out. We'd start by figuring out which ratio are these two sides for theta. Which of the trig functions involve those two sides? Well, this is the opposite, and this is the adjacent, which means we either use tangent or cotangent, right? A couple of you just put in tangent. So we can use tangent or cotangent, but we're going to use tangent. Because obviously we know about inverse tangent. We haven't created an inverse cotangent. So let's just use tangent. So I know that the tangent of theta is 6/8 or 0.75. So in order to figure out theta, I now need to use inverse tangent. So theta is going to be the inverse tangent of 0.75. And this is where we're going to use our technology. So your calculator, or your phone's calculator, or whatever you've got, will have an inverse tangent.
Let me show you where it pops up on my TI-89 because some of you have similar calculators. But if you look on there, there's a button that says tangent. Like pretty much every scientific calculator will have a sine, cosine, and a tangent. And then the secondary function on it, you'll see tangent with a little -1. That's inverse tangent. And I think I warned you about these when we first started talking about how that's not cotangent. So now you see what it is. It's inverse tangent. So what we can do, if we want to calculate this, is you would just go, well, let's find the inverse tangent of 0.75. Now, this is another place where it's definitely going to matter if you're in degrees or radians. If your calculator's in degree mode and you hit enter, it's going to give you an angle in degrees. If you're in radian mode, it will give you the angle in radians. So mine's currently set up for degrees. I'll do it both ways. But in degrees, this is, if I round to the nearest tenth, it's 36.9 degrees. So we know that theta then is around 36.9 degrees. If I was in the other mode, if I was in radian mode, let me just change my calculator that real quick. So I'll go ahead and hit this in radians, and I get 0.6435. So just remember that those are both equivalent. They are both equally valid. It's just two different measuring schemes. It's like if I were to ask you the distance between the Y and state line, you could give it to me in miles, you could give it to me in kilometers, you could give it to me in inches. Please don't. But you could give it to me in lots of different ways, and it's still an accurate measure of that distance. Same thing here. You give it to me in degrees or radians, and they both mean the same thing. All right, so it's about 36.9 degree angle of elevation. So if that was something you were concerned about or you wanted to figure out, we now have a way. Now, you might look at this and go, well, that's silly. I don't care about the angle of elevation to the sun. right? I know this is probably not something that is specific to you, but there are things, anytime you want to find an angle and you don't have a protractor, this is how you're going to do it. So people that do care about this, surveyors, architects, structural engineers, am I starting to catch anybody? Right? Anybody that cares about angles at all, this matters. Now, to someone like me, this question is interesting because I'm really big into navigation. I'm all about, one of my hobbies is actually geocaching. I go out and I find Tupperware in the woods using billion-dollar equipment. But latitude and longitude is all about this, finding positions to the sun. So let me just, Amber just said, so you know to use the inverse when you're looking for the angle and only have the sides. Yep, that's exactly right. So if all you have are sides, all you have are side lengths, this is how you find your angle. So think about real world. Side lengths are pretty easy to measure, right? We have rulers, we have tape measures, we can pace it out. Angles, not so much. And so in the real world, this actually happens a little bit more frequently, where you're trying to find angles given lengths. All right, so how are we feeling about this stuff? Not too bad. I mean, you see the point of it, I hope. And just recognize that all we're doing is going backwards. We just had to be tricky and mark that our angles were only in these restricted places. Okay, well, let me show you why we have to worry about that, this whole restricted thing. Let's go back to what happens when we compose, right? So like if we take inverse sine of sine, they're supposed to cancel each other out, right? And the same thing if we do cosine of inverse cosine and things like that. Well, here's what I want you to do. If you've got your calculator handy, I want you to do two things, and I'll write them on the board so you can see them. But the first one is going to be, I want you to do inverse sine of 5 pi over 7. So we're going to do inverse sine of 5 pi over 7. So I'm giving you an angle, but then you find the sine of it, and then you do the inverse sine. Okay, and then at the same time, we're going to do inverse sine of, let's go, pi over 5. Okay, so we're going to look at these two things. Let me go to the board real quick.
So you can see what I was talking about. So we're going to do inverse sine of 5 pi over 7, and then sine inverse of sine of pi over 5. Now think about what we've seen with inverse functions is that when we compose them, they're supposed to cancel each other out. So what we should expect to see, that we're going to get pi over 5 for the second one, and we're going to get 5 pi over 7 for the first. Because that's kind of the whole point of inverses, right? They just cancel each other out. All right, so let's do this on your calculator. So if you've got your calculator, do the second one first. Let's do sine inverse of sine of pi over 5. So I don't know if you can read it on my screen.
The glare is a little bit rough, but if you look in there, you can see that I'm just doing the inverse sine of 5 pi over 7. Or sorry, pi over 5. So I'm in radian mode, and I need to be in radian mode because my angle's in radian mode. But I hit enter, and what do you get? So I see a bunch of people giving me 0.628. And my calculator agrees. It's 0.6283, whatever. So is that pi over 5? So if you just do a decimal approximation for pi over 5, you should see exactly the same thing. So it worked, right? No big deal. Well, now do sine inverse of sine of 5 pi over 7. What do you get? So Kai says 0.898. Kiva agrees. Okay, so is that 5 pi over 7? You can see if you're looking at the chat window, Kai just wrote, but 5 pi over 7 equals 2.24. Okay, uh-oh. What the hell happened? Because they should cancel each other out. But what we're getting out, that number 0.898, is not at all 5 pi over 7. Crap. Okay, well, this is because we had to get tricky with inverse sine. So let me show you what's going on. I'm going to go to the board.
So when you did sine inverse of sine of 5 pi over 7, you did not get 5 pi over 7. It was not equal, right? Because like Kai said, he saw that 5 pi over 7 is around 2.24, but the value you got on your calculator was 0.89 something. All right, well, let me show you what's going on. So we're looking first at the sine of 5 pi over 7. Let's think about where 5 pi over 7 is. So it's 5/7 of the way over, because 1 pi is halfway, so it's 5/7 of the way over. So it's somewhere over here. Let's just say that this is 5 pi over 7. Okay, so Kai just said, is it because we need to reduce the 5 pi over 7? And the answer to that is no, actually, it's not because of that. It's all because of where we are. So think about inverse sine. Do you remember what angles we had to restrict ourselves to? What was the restriction for inverse sine?
Negative pi over 2 and pi over 2.
Okay, so it was between minus pi over 2 and pi over 2. And the problem is this angle, 5 pi over 7, is not in there, right? It is not in that interval. So that will never be an angle that we get from inverse sine. Inverse sine is only going to give us angles that are over in quadrants 4 or 1. Those are the only choices. So basically what we have to do here is think about what quadrant in the first or fourth quadrant, or what angle in the first or fourth quadrant has the same sine value. So let's do this. Let's kind of slow down a bit. Sine of 5 pi over 7, is that going to be positive or negative? Thumbs up for positive, clappy clap for negative. All right, I'm starting to see thumbs up. Good. Okay, because it's going to be positive, all students. So this is going to be a positive sign. All right, so then which quadrant, 1 or 4, also has positive sign? Thumbs up for 1, clappy clap for 4. Which of those is positive sine?
Can you ask
All
the
right,
question again?
yeah, go ahead.
Can
Oh.
you ask the question again?
Yeah, so which quadrant, 1 or 4, also has positive sine?
Quadrant 1.
Yeah, so it's quadrant 1. I'm seeing lots of thumbs up, ones. It's definitely quadrant 1, because remember, everything in quadrant 1 is positive. Okay, so what angle is that? What angle in here has the same sine value as 5 pi over 7? Would it help if I ask what's the reference angle?
2 pi over 7.
Because that's what this means, right? That's what reference angle is. So we're looking for the reference angle here. So I know the sine of 5 pi over 7 is actually the same as the sine of 2 pi over 7. And now that actually is in the interval where I'm allowed. So in essence, I can change my original question to what's the sine inverse of the sine of 2 pi over 7. And because this is in the correct interval, it's going to give me 2 pi over 7. And if you find the decimal equivalent of that, you'll see that that is that 0.89 whatever that we found originally. So this sucks, right? This sucks. We want to be able to just cancel inverse sine and sine, right? We just want to be able to cancel these things off like we do other inverse functions. And we can't always. We can only do it when we're in the right interval. So I just saw your note, Kai. Then yes, that is what we needed to do. Okay, so I know that this kind of sucks, but it's just something we have to watch out for. We have to see if the angle that we're starting with, if that's not in our interval, if it's not in the restricted interval for our trig function, we have to find the one that is. All right, I wish I could, be all rosy and be like, it's not a big deal, but it is. It's something we're gonna have to watch out for. Just check it. All right, so there are consequences to this. We're just gonna fake out ourselves and make this thing one-to-one. And this is the primary issue, is that when we compose, we don't always get the angle that we started with.
All right, so this is inverse trig functions. Now there's a little bit more we need to do with them. We need to do what's called mixed composition, where we take, say, a cosine of an inverse sine or an inverse tangent of a cosine or things like that. But I don't really have enough time since we're going to have a quiz today as well. So I'm going to go ahead and pause where we are in terms of lecturing. So if you're playing along at home, this is section 8.3. And I think maybe we're starting to go into 8.4. I don't know, or somewhere in there. But we're definitely in the inverse functions area. So I'm going to pause the recording. Right again. Because Juan just reminded me that we do need to have a word of the day. I'm really glad that you guys pay attention to what should happen in class, because I have no clue. All right, so word of the day, because again, it's got to be something that I've got kind of handy. The word of today will be magnet. Magnet will be your word of the day. Okay, so word of the day is magnet.